So now when you're looking at schematics, resistors, these are what the physical components look like if they're 3 holes, tend to be jagged lines right there with their values next to them. 1K is the same as 1000 ohms, although it may be in rectangle form right there. If it's like 4700, which is 4.7K, often the K will be placed where the decimal point is because you may not see a decimal point on there. If they're higher wattage resistors, they should say the wattage right there. But again, learn wattage so you can make sure that you're not using a component that is too low in wattage. So of course these have the color code there. The typical through hole is a quarter watt. If you just buy a bunch of resistors, you're probably going to get quarter watt unless you look for a different wattage. Still recommended to stay below half of that, an eighth of a watt. So that's 0.25 watts. Quarter watt, 0.125 watts is an eighth of a watt. So now, diodes are common components in electronics, mostly the LEDs these days though, but also there's a lot of important diodes. So rectifier diodes, this is the basic symbol right there. It may come in the plastic package. Cathode is where the band is, or the glass package right there. Anode over here, that's how you indicate those. When it comes to the LED, the anode usually has a longer lead, cathode shorter lead, and often a little shaved edge right there. Again, the symbol. You need to have the diode forward biased in order for it to conduct easily. So that's called forward bias. Anode's more positive than the cathode, more negative, but you got a resistor to limit current. Diodes don't limit current on their own. And then there's reverse. That's when you want to cut off the conduction right there. And you should use a resistor that can limit the current enough to protect both it for its wattage and the maximum current of the diode, especially LEDs. For lighting them up. 470 ohms should work pretty well with 9 volts. So now, capacitors come polarized. You have to charge them in the proper direction, and non-polarized. You can charge them in either direction, both directions even. And one of their main uses is, in this case, you could close the switch, instantly charge the capacitor, and power the load. You got to make sure you don't use too high of a value capacitor because it's kind of like a short circuit while it's charging. But if you briefly lose power or something, the capacitor will pick up the slack and keep the load from really changing, as long as the capacitor value and resistor will allow it to do so. That's RC time constant. Current goes one way into the capacitor while it is charging. And once it gets to the voltage that is charging it, or you cut off voltage or whatever, it's going to store that charge as long as there's nothing draining it right there. When you got something draining it, usually there's like a load going to ground, then current goes in the other direction. It's kind of a way to make AC. So now in basic electronics, usually you're using a single supply. Let's say you got a 9-volt battery, the negative side is ground, then you got a positive voltage in relationship to that. That's the battery voltage, 9 volts right there. And you design your circuit to kind of be within that voltage range right there. If you want a negative voltage in relationship to ground as well, you can take a second battery. So instead of them being in series, which gives you 18 volts, instead you have all your other circuitry end their path right here. Maybe they come from the positive side right there, and maybe they come from the negative supply, but they get back to ground. So if you look at a circuit where you see something like that, that's what it's doing. Some components have current going that way, and then other components have current going the other way, but in a completely different path right there. So now, common battery combinations. First, you got the single one. If it's a 9-volt battery there, usually consider the negative supply ground and the positive supply the voltage difference right there, positive 9 volts. You can put them in series to add up their voltages. 18 volts total because they are in series. They're both pushing right there. Not to be confused with a split or a dual supply right there, where the middle point is ground. You have a negative voltage and a positive voltage in relationship to ground. You could have that. Now, the reason why you would parallel batteries look something like this, positive, positive, negative to negative, is because then each one's providing about half the current to the load. Make sure they're the same voltage when you connect them together. So you'll be able to power it twice as long. It's like having a 9-volt battery with double the capacity. Of course, you can do parallel and series combinations right there to get the double the voltage to last twice as long, or again to have a split supply that will last twice as long. So now keep in mind that some components can be connected directly to a power supply that do something. That would be incandescent light bulbs. They create light. You disconnect them directly to a voltage designed for them. Be aware of that. LEDs are not one of those components. You need a resistor to limit the current to protect the LED. With 5 volts, 220 should work well to limit current and keep the resistor from getting too hot if you're using a quarter watt. 12 volts, you probably want at least 1,000 ohms to protect the LED. And if you're using 9 volts, then probably 470 is pretty well to protect the LED. Now there's LED modules that are used to, I call them modules, used to replace incandescent light bulbs. They usually have a built-in resistor. So in those cases, you can connect them to a voltage they're rated for directly, but they have a resistor built in. So now when it comes to basic circuits and timing, generally you use a capacitor and a resistor right there. You can charge the capacitor and then have it discharge through the resistor when you stop charging it, and you can take the time to do stuff. You can look at the voltage and whatnot. We'll zoom back and look at another version. 10 times the capacitance, 1/10 the resistance, gives you the same timing. Hopefully that makes sense. So we'll zoom in. So if you're working on, well, whether it's charging or discharging, you take the value of the capacitor in farad times the resistance, and you get your time constant right there. So both examples are the same right there, and the symbol is tau when it comes to time constant. So in this case, it is the discharging that's going on. We're going to lose about 63% of the voltage in the first time constant of 1 second in this case. So each time you're going to lose about 63% of what's left. So ultimately you need 5 of those time constants to totally discharge. So now sometimes you want to use a charging capacitor for the RC time constant. So we could discharge the capacitor by the closed switch. When we open the switch, the capacitor will charge through the resistor. We could use, 1/10 of the value of the capacitance and 10 times the resistance to get the same amount of charging right there. Doesn't really matter. It is the capacitance in farad times the resistance in ohms that gives you your time constant. We got 1 second again. So again, the time constant, which is the symbol tau right there, same as resistance times capacitance, is how long it's going to take to make a 63% voltage change from your starting voltage to your final voltage. That's 63%. So the next time constant is going to do what's left over, 63% of what's left over. So ultimately it takes about 5 of them before you get from your starting voltage to your final voltage, in this case charging. So now one way to use the RC time constant, so that's resistor, capacitor, their combination to do something useful is to keep an LED lit for a brief period of time when you cut power from the power supply right there. So you got the stored charge of the capacitor, it's going to flow through the LED and keep it lit, but it will dim down pretty rapidly right here. This is a more simplified schematic of that. And so if you need longer periods of time, you could use this RC circuitry to put a little bit of current through a transistor, which will be on, and the LED will be on for a longer period of times. All kinds of ways to improve this. But yeah, this is a basic demonstration circuit that I do. When I close the switch, capacitor instantly charges, and the LED is lit. When I open it, then the LED fades off pretty quickly. So now when it comes to measuring voltages, especially for the first time, it's good to get practice with simple circuits. So you can measure the voltage of a battery. If you have a 9-volt battery, you just put the probes across the battery right there, set it to measure voltage, digital meter, and you should see 9 volts in this case right there, using a digital multimeter. That's really all people use these days. If you put it backwards, you'll just get a negative voltage. That's all it's telling you is the probes are backwards. Perfectly fine. So yeah, 12-volt battery, again, yeah, you should measure that it's like 12 volts. Now, when it comes to how much current's flowing through the circuit, the resistor sets that, but the LED does drop a couple volts. You can measure that with the multimeter right there. That leaves 10 volts across the resistor for setting the current. 10 volts divided by 1,000 ohms is 10 milliamps of current. So that's how much current's going to flow through this circuit. So it's important to understand voltages and therefore measuring voltages with the multimeter. So now usually circuits are controlled by something. You could have a switch. This is a symbol for a push button switch, but any type of switch could use. And they don't usually show a finger there other than me to indicate that you're pressing a push button switch. So while it is open, there's a gap, then current can't flow. And most push button switches are open when you're not pressing the button. And then when you press the button, then you close the gap. So while the switch is open, no current is going to flow. And then when you close the switch, then current is going to flow. And at that point, the switch is just a connector right there. It's a connection. So at that point, then the current's going to be set by the load and the supply voltage right there. So if this is easier to see for a short, then I will turn it in this direction right there. So even though the numbers are sideways, it's the same circuit, of course. So now in this short, we're going to combine a common switch and a capacitor. So we have the single pole double throw. There's one spot that's always connected, but it jumps from one position or the other. So we could instantly charge the capacitor right there. It'd probably be better to put the 1000 ohm resistor over here to set the timing for the charge. But in any case, that's what we have. Now we can flip the switch over there. Since the resistor's there, that's when the capacitor will discharge through the resistor. So it will take time, but you'll be able to light an LED while doing so. So again, this is not a great circuit. You should improve on it, but always think that way when you're looking at schematics. It's not how you have to build the circuit, it's just giving you ideas. So 1000 microfarad right there is the same as 0.001 farad. That's what you use when you do the math right there. And it's also the same as 1 millifarad, but usually the values are given in microfarads. So now, you can always add capacitors in parallel next to each other to add up their capacitances. When it comes to series capacitors, usually there's a more important reason why you're doing so. Capacitors have a maximum voltage that they can be charged to. If you have polarized capacitors, it may be 50 volts right there. But if you want to charge a capacitor to like 100 volts or something, then you cannot do so with one of these. You can't exceed the rated value. But if you put them in series, then they will both charge at the same time. They'll both get, let's say, 50 volts. And then when you add up those 50 volts, they have a total of 100 volts, but the actual component is only getting 50 volts each. Now, they also charge at the same time right there. Their voltages are going up together right there. So as far as the rest of the circuitry is concerned, it thinks it's only half of the capacitance right there because they charge and discharge twice as fast. So now once you get past the very basic circuits, you're going to see voltage dividers here and there. So typically they're made up of fixed value resistors, or commonly I should say. And if you got two equal value resistors with a voltage across them, where they meet in the middle, you're going to get half of that voltage. So in this case we got 6, you're going to have 3. That's not the power stuff though. That's just a voltage for other circuitry to look at and respond to. If you got 3 equal value resistors in series across the load there, where they connect together towards the high side here, you'll have 2/3 of the supply voltage because 2/3 of the resistance is headed towards ground. Down here, you'll have 1/3 of the supply voltage because 1/3 of the total resistance is headed to ground. So there's components called potentiometers or trim pots. It's one resistive element, but there's a wiper that slides up and down. So you can get whatever percentage of the supply voltage out that you want. So now, in a previous short, we looked at how capacitors have a voltage limit. Everything has a wattage limit or a voltage limit. But in any case, if you want to charge a capacitor to more than, in this case, 50 volts, you need a couple in series right there. They will have an equivalent of like half the resistance though, because they'll both be charging at the same time. But their voltages add up, so you can get a higher voltage than either one alone. Problem is, one of them may charge quicker than the other for whatever reason. The other one might have a little leakage or something. It discharges a little bit. They can become unbalanced, and so you might get more than 50 volts on one of them, even with 100 volts. So the voltage divider can come in here. You know, it divides up the voltage from the supply, helping to keep them equalized right there. If one starts getting a little bit higher voltage than the other, it's going to like discharge a tiny bit and lower its voltage while raising the other one. Whichever one has the higher voltage is going to discharge a little bit more. So of course you can improve on this, but this is the basic principle. So now, if you have a circuit that responds to light, a lot of times you use a light-dependent resistor. So its resistance changes depending on how much light is falling on it. More light, less resistance. When it's darker, there's more resistance. Often use it as a voltage divider. But often that light is not steady. It's kind of flickering, even though your eye may not notice it. So what you can do is just take your voltage divider right here, put it to a capacitor. So it may take a split second to get to the final voltage, but ultimately it will help smooth out any rapid changes right there. And you'll get a more steady voltage for other circuitry that depends on a steady voltage to keep from like oscillating or something. So another light-dependent component is the photodiode. You use a reverse bias. It looks like an LED, but however much light is falling on it will determine how much current it will let flow through. You can use a series resistor if you want to limit current to a maximum amount. And also, you could have a series capacitor. If the capacitor is fully charged, of course, no current's going to flow. So you discharge the capacitor right there. When you open the switch, though, you're going to have a steady amount of current flowing based on the light level. If the light level changes, it won't be steady. But if the light's steady, then you'll have a steady amount of current. And the voltage is going to rise steady because capacitors, voltages rise as the current flows in. Current is steady, so the voltage rise. Now, if you have more light, of course, the voltage is going to go faster. But also, if you use lower value capacitors for a given light level, the voltage is going to rise faster. So you can adjust it in those ways. So now, oftentimes you'll have a value of resistance that you want, but you don't have a resistor that can meet that demands for whatever reason. So what you can do, you can take lower value resistors, connect them in series, and you take their total resistance, add it up, and that will work. So you try to get the same amount of total resistance. Now, these resistors should not be in a 9-volt circuit. We got 9 volts there. The LED does drop about a couple volts, so we got 7 volts. But now they're dividing it up even further. Always remember, series resistors are voltage dividers. So the one with about 2/3 of the total resistance is going to be somewhere about 2/3 of the remaining voltage across it. Whereas the one that's about 1/3 of the total resistance is going to have about 1/3 of the remaining voltage across that. We got, kind of off here because of rounding. We dropped about 2 volts there in my math. But there you can see. They split up the voltage, so they don't have as much voltage across them as you may think. So now, we're going to look at what you can do if you really want about 10 milliamps of current through a circuit, at least for calculating how much resistance you're going to need. So, you got to remember, if you're protecting an LED, red LEDs drop about 2 volts, blue LEDs about 3 volts. For the red LED, if you're using 5 volts right there, you're going to drop about 2 with the LED, giving you 3 volts across the resistor, which will set the current. Your desired current is 0.01 amps, 10 milliamps. Then when you do this math, you'll see you need 300 ohm resistor. It's pretty straightforward there. They don't generally come in 300 ohms. You can take series or parallel resistors until you get that equivalent resistance. Now with the blue LED, it drops about 3 volts. So out of 5, you got like 2 divided by 0.01 amps. Gives you 200 right there, ohms of resistance you're going to need. Again, probably won't find that exact value, but you can do series and parallel connections until you get it. So now, if you want to light multiple LEDs, it's not a good idea to connect them parallel like this. You'll have the current setting the resistor setting the current, and it'll be split up among the LEDs, but maybe not equally, even if they're equal LEDs right there, same color. So again, current will go through, set by the resistor, but then it will split up between the two. But maybe not equally, and definitely not equally if one has a different forward voltage. The one with the lowest forward voltage will definitely pass all the current. So what you do is you simply just give each LED its own resistor. So now the LEDs are in series with the resistor, but the LED and resistor is in parallel with the other LED and resistor. The resistor will limit the current through that one, and the resistor will limit current through that one. They will not affect each other in any way. So now, I use 1,000 ohm resistors in my videos quite a bit. The voltage across it, and divided by its resistance, gives you the current. So, pretty simple when it comes to current. For each volt, you're going to get 0.01 amps of current. 0.01 amps is the same as 1 milliamp. So, 3 volts across the 1000 ohm resistor, you get 0.03 amps. Pretty straightforward there. Remember, wattage goes up a lot quicker than either voltage or current, because it's voltage times current. So we can pretty safely put 11 volts across the resistor right there, giving us 11 milliamps of current, 0.12 watts of power. So a quarter watt resistor, 0.25 watts, should still stay below half of that. And we got that there, even though we are somewhat close. So if you're protecting a blue LED, it's going to drop, from 12 volts, it's going to drop 3 volts for 9 volts. If you're protecting a red LED, from 12 volts, it's going to drop 2 volts, giving you 10 volts. So now, I use 220 ohm resistors a lot in my videos. The voltage across the resistor divided by resistance gives you the current, basic resistor property. So here you can see, if you got 1 volt divided by 220 ohms, that gives you a 0.0045 amps estimated, or rounded off I should say, or 4.5 milliamps of current. You double the voltage, you'll get double the current, 3 times the voltage, 3 times the current, and so on. Remember though, wattage is voltage times current, so it goes a lot faster, it rises a lot faster. But we can put 5 volts across a 220 ohm resistor, 22.7 milliamps of current. The wattage is only going to be about 113 milliwatts. We can go up to about 0.125 watts, which is the same as 125 milliwatts. So the resistor won't get too terribly hot. Of course, red LED is going to drop about 2 volts, and so it'll be even better. And then a blue LED will drop about 3 volts, so even safer there. So now, I don't use 100 ohms a lot in my videos. Again, with the resistor, the voltage across it divided by its resistance gives you the current. So you got 1 volt divided by 100 ohms. It's going to give you about 10 milliamps of current. 1 volt divided by 100 gives you 0.01 amps in this case, which is the same as 10 milliamps current. Of course, you double the voltage, you get twice the current, 3 times, and so on. Now, we can't go terribly high on voltage because we're getting relatively high current right there. So the wattage gets up to about almost 0.125 watts, which is kind of where we want to limit it. Half of the maximum wattage of 0.25 watts right there. But as long as you can cut down the voltage across the resistors in some way, you can get, a relatively high amount of current for low power circuits. So many times I use 1000 ohm resistors in my circuit, especially for like 12 volts, because if you're protecting a red LED, in this case, you're going to have 10 volts across it, 10 milliamps of current flowing through it. The math down there, pretty straightforward. 10 volts across it times 0.01 amps, which is the same as 10 milliamps, is 0.1 watts. So that's kind of the limit you want to set, close to the limit. Power for a quarter watt resistor, which is 0.25 watts. This is a little bit below half that, which we kind of want to stay. So if we want twice the current, we have the option of just putting another resistor parallel. So each one of them is going to pass 10 milliamps of current. They're both going to get to this wattage. But those currents are going to combine, and they could go through in the LED in this case, which is pushing its limits, 20 milliamps. But you can do so. So here's a pictorial of how that looks. So if you need more power, oftentimes it's easy to just parallel resistors right there.